continue with the review of atomic bonding. We have looked so far at the strong bonds, we have discussed the ionic bond, the covalent bond and the metallic bond. Now, we look at the weaker bonds, the van der Waals bonds and the hydrogen bonds, and then we will go on to see how the type of bond affects the behavior of the element or the material. Now, in van der Waals bonds, we have a weak bond between the atoms and molecules. We have to look at the electrical configuration of the atom to understand how the van der Waals bond forms. Over a period of time, we find that the atom is electrically symmetric, that is, the center of the positive charge and the center of the negative charge coincide, the positive charge coming from the protons and the electron cloud giving the negative charge. At any instant in time, what we find is that there is a distortion in this electrical configuration. We could imagine that at a particular instant there are more electrons, or there is a more of a negative charge on one side of the atom and the positive charge is on the other side. So, the center of the positive charge and the center of the negative charge do not coincide at any particular instant of time, and this induces what we call an atomic dipole, where the positive charge center and the negative charge center are separated by a certain distance, giving rise to this dipole. So, this we can imagine is occurring at any particular instant of time. This is changing continuously and therefore, it is dynamic. So, as I have said, the electron charge spread around the atom is symmetrically distributed over a period of time. However, at any particular instant, in time, this electrostatic field is continuously moving, fluctuating, and this gives rise to these dynamic electric dipoles. Dipole meaning that the centers of the positive and negative charge do not coincide. So, we can see that now instead of the atom being always electrically neutral, at particular instant of time we have a charge non-symmetry with one end being more positive and the other end being more negative. And when you have atoms interacting with each other, one atom coming close to another atom, we could have the dipoles interacting with attractive forces occurring between the atoms when the negative charged end of one of the atoms is attracted by the positive charge end of the other atom. So, as we have said here, when two atoms are brought into proximity, that means when they come close to each other, the dipoles of the two atoms interact, resulting in a weak non-directional electrostatic bond. This is a weak bond and this again depends on the distance r between the two atoms that are interacting. So, these were the dipoles that we saw being generated due to the instantaneous distortion of the electrostatic field. This gave rise to one end being more positive, the other end being more negative. For example, here you see that there could be more electrons on this side, shifting the center of the electrical charges to the left, the right side becomes more positively charged. In this case, you have the opposite happening, you have more of the electrons in the other side at a particular instance, and we have then the positive charge side being attracted to the negative charge side of this atom. The attractive forces between the two atoms due to van der Waals bonds is given by this as a product of alpha 1 and alpha 2, which are called the polarizabilities of the two atoms, divided by r, which is the distance between the two atoms, raised to the power of 6. So, it is alpha 1 times alpha 2 divided by r to the power of 6. And what we find is that as the distance between the atoms increases, the attractive force decreases by a power of 6. That is why it is called a very weak bond, because even a small increase in the distance between the atoms decreases the attractive force between the atoms very significantly. The polarizability, that is the alpha values, increases with atomic number. That is, as the atomic number increases, the valence electrons are further away from the nucleus. We can imagine that the atom is bigger, the valence electrons are farther away from the nucleus, and so when they are moving around, there is more distortion of the electrostatic field and they can be pulled more easily towards the neighboring atoms also. So, this polarizability alpha increases with the atomic number. Higher the atomic number, more would be the polarizability, and therefore, more would be the attractive forces between the two. Van der Waals bond, even though it is a weak bond, is responsible for a lot of phenomena, including viscosity and surface tension that we will look at later. The heat is something which can break Van der Waals bonds easily, which explains the boiling of liquids, how liquids become gases, the melting of thermoplastic materials with the bonds separating very easily due to the heat energy. So, all these phenomena can be explained. Look at Van der Waals bonds. A specific type of Van der Waals bond that is stronger is the hydrogen bond, where we have a very strong dipole interaction when the hydrogen atom is involved. And this we can imagine because of the size of the small hydrogen atom. There is a big distance between the positive and the negative charge of these molecules coming about, because the hydrogen atom is much smaller than all the other atoms. So, you have a dipole that is very easily formed between the hydrogen and any other element, for example, here chlorine, where you have the positively charged end of the dipole coinciding with the hydrogen atom, and this, due to the specific nature in which hydrogen bonds, is directional, and this gives rise to specific structures. For example, in the bonding of the ice crystal, you see a certain type of configuration with a lot of space in between. The hydrogen bond, since it is stronger than the other Van der Waals bonds, is also responsible for giving a high melting point to ice and a high boiling point to water. The hydrogen bond also contributes to good mechanical performance, high mechanical performance and high heat resistance of some polymers which have hydrogen in them. For example, nylon and Kevlar, which have higher mechanical properties, superior mechanical performance than other similar materials bonded just with Van der Waals forces. Now, let us look at the different bonds that we have considered. We looked at 3 strong bonds: the ionic bond, the covalent bond and the metallic bond. This column gives the bond energies. Higher the bond energy, the stronger is the bond, and we see here that the ionic bond has much higher value than the others, 500 to 1200 kilojoules per mole, and the covalent bond has a range that is lower and the metallic bond lower still. Typical materials that have these bonds are: in the ionic bond we have a lot of salts which exist as crystalline solids. Covalent bonds, we looked at the examples of silica and diamond. There are other materials such as polymers which have covalent bonds, metals, elements in groups 1 to 3, transition metals, heavy elements of group 4 and 5 and so on also have metallic bonds. The two weak bonds or the secondary bonds that we looked at were the hydrogen bond and the van der Waals bonds, and between the two the hydrogen bond is stronger, has about 10 to 30 kilojoules per mole, and we have the van der Waals bond which is slightly weaker. Water is a typical example of a material having a hydrogen bond, and van der Waals bonds are there in all materials wherever we have atoms and molecules coming together. So, these are primarily what we call intermolecular bonds, and they dominate the behavior even though they are weak bonds, they dominate the behavior and microstructure of many construction materials including concrete and asphalt, where the microstructure is held together by these van der Waals forces. Now, a material need not have just one type of bond in it. Most materials the bonding is a mixture of 2 or even 3 types of bonds. For example, in plastics, in polymers we have covalent bonds within the chains, and the chains are held together by van der Waals bonds. In metallic alloys we have both covalent and metallic bonds, and we have van der Waals forces across the grain boundaries across the different crystals forming the metal. In ceramics we can have both metallic and non-metallic elements, and these can be covalently and ionically bonded with again van der Waals bonds across the grain boundaries. So, many of these bonds can coexist and do coexist in the materials that we consider. Now, let us look at how these bonds and the type of bond and the relation between the potential energy and the interparticle distance, how they do affect the properties or the behavior of the material. So, if we look at an ionic bond, a strongly bonded solid that you see on the left, we have this diagram that we looked at initially, where we have on the y axis the potential energy or the lattice energy in terms of a crystal, and on the x axis we have the interparticle distance, the interatomic distance or the interparticle distance. And as we said in the beginning of this lecture, when the atoms or particles come together, there is an attractive force, there is an energy that is attributed to the attractive force. This is pulling the atoms together, and this force or this energy increases as the distance between the atoms decreases. Very far away there is a weak attractive force, and as we are coming together this attractive force increases. Now, there is also a repulsive force, and this repulsive force becomes very high when the atoms are very close to each other. If we push the atoms together a lot, you have a very high repulsion occurring, and this overtakes the attractive forces when the distance becomes very small. What we see here in the dark line is the resultant between the attractive part and the repulsive part, and this dark line now gives the potential energy with respect to the interatomic space, interatomic distance, or in a crystal the lattice energy and the interparticle distance, the interparticle distance being r. And what we see now is a typical shape of this diagram, where you have, as the interparticle distance decreases, the lattice energy decreases, reaches a minimum at a certain configuration defined by an interparticle distance r0, and then when the atoms or the particles are pushed closer to each other than this r0, we find that now the repulsion becomes more and more, and if you go very close the repulsion is much more than the attraction. So, for a strong bond, say in an ionic bond, you will find that this part is lower, that is the lowest energy that we see is more. So, this part which is called the well is deeper for a more strongly bonded material. We have also a similar diagram, but different values in the case of a weakly bonded solid. We find that the diagram is similar, we have a similar shape, but the value of this minimum lattice energy is less, that is this well is less deep or shallower. What we find also that there is more asymmetry in the shape of this well in the case of a weak bond. In the case of a strong bond, we saw that it was deeper and came up like this. In this case, we have a well which is shallower and you have a more pronounced asymmetry around this part. Here you see that the asymmetry is less than in a weak bond. So, we see that there is a difference in how the energy particle distance occurs in a strong bond and a weak bond, and when we compare these two diagrams we start understanding other aspects that we will deal with in a minute. This diagram is called the Condon-Morse diagram, and this gives us now the net attractive energy between different particles as a function of the distance between them. And as I said before, the depth of the well indicates the strength of the cohesive forces. The deeper the well or the higher or more is the minimum potential energy, we have a stronger bond. And the value of R, which is the interparticle distance that corresponds to U minimum, is the interatomic distance R0, where there is an equilibrium between the ions in the crystal. So, that is the most stable state. These distances are not very large, they are sub nanometric. Primary bond lengths, that is the strong bond lengths, are lower, they are in the order of 0.1 to 0.2 nanometers. The secondary bond lengths are slightly more, 0.2 to 0.5 nanometers, but still we are talking about a nanometric scale. These are very small distances that occur in the molecular level. Now, in terms of the properties, we know that the boiling point of a material is proportional to the value of U min. That is, as the well or the minimum energy is more, the boiling point of a material is higher. That is, we need more energy to separate the bond when the bond is very strong. We also can look at the force displacement behavior or understand the force displacement behavior when we look at the Condon-Morse diagram. When we differentiate the diagram between the energy and the interatomic distance, we find that we get the force diagram. Here on the lower part of the screen you see the Condon-Morse diagram giving us the potential energy versus the distance or the separation between the atoms. Now, when we differentiate energy, we get the force. So, we get the diagram at the top, which is giving us the force between the two particles or the two atoms, where here the curve labeled as F A gives the attractive forces. showing that as the interparticle separation decreases or the atoms come closer together, there is a higher attractive force. This was what was giving us this bottom part of the potential energy. When the atoms are very close to each other or we push the atoms together, then we have the repulsive forces. The resultant of these two is given by this diagram. So, here you find that at the point where we had the trough of the well coincides with the 0 force, we find that the diagram is symmetric about this point, that is, we have a similar behavior very close to the stable interparticle distance r 0 when we go either in compression or in tension. Okay. So, if we are going to the left, that means we are compressing the solid, at r 0 the solid is at its stable state. When we are going to the right and increasing r beyond r 0, that means we are pulling, separating or applying tension. And if we remember that, we can see some interesting things. When we pull on a solid or we try to separate the solid, we find that as the solid is stressed, there would be a linear part which would be the elastic part, then there is a non-linear part where you have a non-linearity, then afterwards you reach a peak value which is giving us the tensile strength of the material, and then afterwards when we continue to stretch the bonds more, when we continue to separate the bonds further, we find that the forces keeping the solid together decreases and finally becomes 0. That means the material has completely broken or the bond has broken. When we go to the other side, when we try to decrease the interatomic spacing, that is, we are compressing or pushing the atoms together, we find that there is the repulsive part that is dominating, and we find also that the repulsive forces keep increasing as we push the material closer together. We also find from this diagram that failure can never occur in pure compression, because you are getting higher and higher repulsive forces. So, materials will never break when we have only compression acting on the material, because the repulsive forces become very, very high. So, to summarize this diagram, the bonding force can be given by the derivative of the energy by the distance or the separation between the atoms. The resulting curve, this curve about r 0, we found that it is linear. This part gives the restoring force that pulls the material back to its stable state, and this part being linear indicates why we have an elastic regime in most materials, and also why we have Young's modulus both in compression and tension which are equal. So, some of the consequences are that the FR diagram, the diagram of force with respect to the distance, is symmetric at r 0, about r 0, and the elastic modulus is almost the same in compression and tension. So, in most materials we assume that the Young's modulus is the same in compression and tension, and we can sort of explain this from the bond behavior in the particle level. At larger strains, we saw that the FR diagram is no longer straight, it becomes nonlinear, and also in most materials that we use, we always see a nonlinear part in the mechanical behavior. As the tensile strain is higher, as we increase the distance between the particles, we pull on the material reaches a point where it ruptures, it reaches a maximum value which we can call the tensile strength, and beyond that the material does not have any forces holding it together and it breaks apart. What we also saw is that under compression the repulsive forces dominate and there is no possibility of failure under pure compression. We can also draw some conclusions on the effect of temperature on the behavior of the material by looking at the Condon-Morse diagram. On the left we have a weak bond and the right we have a strong bond, and if you look at this diagram we see that above the minimum point or this rough we find that there are many positions of R which will have the same energy U. At this point there is a unique interparticle distance R0 where U minimum occurs or the minimum energy occurs, but at other values of energy we have different possible locations where there is the same energy. So, this means that above this point which occurs only at absolute 0 temperature, above this point at any other temperature there are many positions or many interparticle separations which give the same energy. So, this explains that there is an oscillation of movement of particles at any temperature above the absolute 0 temperature over a certain region. So, at T1 the particles can be oscillating with separations over this distance. At T2 this distance is more, so there can be oscillations over a larger distance. At T3 even larger distances you can have the interparticle separation moving about. The average is this dark line. The average distances between the particles at each temperature is given by this dark line, and what we find then is that this average distance for say a temperature T2 will be R0 prime, which is higher than R0. We find that the average distance at any temperature higher than T0 will be always larger than R0, and this is the reason why we see expansion with temperature. What we are seeing here is as the temperature is increasing there is a larger oscillation, and this average of these oscillations or the average of this separation always is higher than R0. The difference between R0 and R prime 0 is the expansion that the material undergoes at a certain temperature T2. And what we find that is in the weak bond, as I mentioned earlier, there is a shallower well and you find that there is a bigger change in the interparticle separation than in a strong bond. In a strong bond around this point there is not much asymmetry. Around this point you see that the well is almost symmetric, and therefore, when you draw the average between this distance you find that initially it is very little and only very high temperatures can cause a larger deviation of the interparticle distance from R0. So, for the same change in temperature you have a smaller variation of the average interparticle distance from R0. So, what we find is that in a strongly bonded material the thermal expansion is less than in a weakly bonded material. So, to summarize, the mean interatomic distance increases with temperature. Only at 0 degrees Kelvin, that is the absolute 0 temperature, we have the potential energy of the solid equal to the minimum possible, where R0 is the interparticle distance. At any other temperature, we find that the interatomic distance changes, keeps changing, and the average R0 is now higher for a weaker bond. For a stronger bond, the well is deeper. We have a narrower well, and therefore, the change in interatomic distance is smaller as the temperature increases. So, from this we can see why strongly bonded solids have lower thermal expansion than weakly bonded solids. Other consequences: as temperature increases, we saw that the interatomic separation increases due to the vibration of the atoms, and this occurs in all directions. That is why when we increase the temperature and you see an expansion in the material, it occurs in all directions. The material expands in all directions when the temperature increases. When we increase the temperature further, we increase the separation between the particles further, and there will be particles reaching a separation where the forces keeping the bond together are broken. That is, the attractive forces are so small due to the large separation that has been created between the atoms that the atomic bond breaks and liquids evaporate. The bond is broken basically by the energy that is put in as heat, leading to a increase in the separation between the particles, and they are not held together anymore and they are separated and the bond is broken. Also, we see that to break a bond at higher temperatures will be easier, because already the bond is separated, the particles have a large distance between them, and therefore, to break that bond at a higher temperature you need less energy. And this is reflected by the fact that the tensile strength of any material generally decreases with an increase in temperature. As you increase the temperature, it is easier to break a material. That means, the force required to break a material is smaller. So, these are some of the consequences that we can understand from looking at the Condon-Morse diagram, comparing how the diagram looks for a weak bond and a strong bond. So, these are some of the references that give you more information about the bonds, the type of bonds, and their influence on the mechanical behavior. So, to summarize, in this lecture we have looked at how bonds are formed and the different types of chemical bonds. We looked at the strong bonds, the ionic bond, the covalent bond, and the metallic bond, and we looked at some of the properties. And in the second half of the lecture we looked at the weaker bonds, the van der Waals bonds and the hydrogen bond, and we saw how the van der Waals and hydrogen bonds are formed because of the dipoles that occur due to the instantaneous distortion in the electrostatic field, where you have a separation between the center of the positive charge and the center of the negative charge. So, this separation between the charges causes attraction between adjacent atoms, and you have the atoms being bonded by these weak bonds, the van der Waals and the hydrogen bond. And we also saw that the hydrogen bond is a directional bond, because the hydrogen atom is bonded in a certain configuration. The van der Waals bond is a non-directional bond, create bonds in all directions, not so the hydrogen bond. Then we went on to see what is the Condon-Morse diagram, which gives us the relation between the potential energy or the lattice energy and the separation between the particles, and we saw how this diagram differs between a strong bond and a weak bond, and we also saw that this diagram has a very distinctive part arising from the attractive forces and another part which comes from the repulsive forces. The resultant is the figure showing us the energy versus the distance. This is non-symmetric, and when we have tensile forces, we find that the Condon-Morse diagram shows us that initially the behavior is elastic, you have a linear behavior between the force and the interatomic distance, then there is a non-linearity, there is a peak value which is associated with the tensile strength, and then when you keep separating the bond, the separation becomes so high that there are no further attractive forces to keep the material together, and ultimately you have failure. On the other hand, in compression we find that when you push the atoms closer together, when you have interatomic distances that are less than r0, which is the value corresponding to the minimum potential energy, you have very high repulsive forces, and the forces that react due to the compressive forces that we apply are very high, and we will never have failure occurring in pure compression. We also saw how we can understand thermal expansion from the Condon-Morse diagram. The well in the Condon-Morse diagram where you reach a minimum value in the potential energy is non-symmetric, and above the point of 0 or absolute 0 temperature, 0 degree Kelvin, we find that there are many interatomic distances which will have the same energy, and so the particles can be in any position or vibrate over any position that gives you the same energy. And if we take the average distance, we find that this average distance now, as we increase temperature, is always more than r0, which is the stable interatomic distance, and as temperature increases, this r0 prime or the average interatomic separation increases. Because of this, we have expansion of the material in all directions as temperature increases. And also we saw, by comparing the Condon-Morse diagrams of the weak bond and the strong bond, that due to the shape of the well being narrower and deeper in a strong bond, we do not have much change in the interatomic separation for a stronger bonded material when temperature increases, well compared to the case of a shallow bond. We also looked at typical bond energies for the case of the different bonds, and we saw that the ionic bond was strongest, followed by the covalent bond, then the metallic bond, then the hydrogen bond and the van der Waals bonds. And we also looked at examples where these different bonds occur, and what we also emphasized is that a material would have more than one particular type of bond. For example, in a polymer we have covalent bonds within the chains, and we have van der Waals bonds between the chains that hold the polymer together. In the next lecture, we will see how the structure of materials develop, linking this development of structure to the bonds, and that will take us little bit more to the formation of the structure, and we will see more of the properties being evident when we discuss the structure of the material. Thank you.